Namaste and welcome to the course on linear algebra through geometry, and in the last few lectures we have been focusing on the vector spaces, vector subspaces and so on, and in the last couple of lectures we focused on the 4 fundamental subspaces associated with a matrix. That means you basically try to look at the set of solutions to the homogeneous system of equations that formed a subspace which we called as null space of A. Then you look at the set of vectors which can be written as linear combinations of the column vectors of the matrix A or the columns of the matrix A. You call that to be the column space of A. Similarly you could do that for A transpose 2, and therefore we had 2 vector subspaces associated with the matrix A and 2 vector subspaces associated with the matrix A transpose, one on each side, I mean 2 on each side. Like you had null space of A as a subspace of Rn, column space of A as a subspace of Rm, null space of A transpose as a subspace of Rm, and column space of A transpose or the row space of A as an element of as a subspace of Rn. And we also looked at some of the definitions associated with the null space and the column space and stuff. We said that the dimension of the null space of A was called the nullity, and the dimension of the column space of A is called the rank of the matrix A. And we also had the knowledge of rank from the previous system of equations concept ideas, where we said the rank is equal to the number of pivot variables in the row reduced echelon form. It was also equal to the number of non-zero rows in the row reduced echelon form of the matrix A. This corresponds to the rank, and essentially from there we could also deduce the fact that the number of free variables corresponds to the nullity, and the number of 0 rows in your matrix. So we basically looked at the number of what would you call the number of free variables plus the number of pivot variables was equal to the number of columns, and that is basically what we said. It is the rank nullity theorem, where we said the rank of a matrix plus the nullity of the matrix is equal to the number of columns. In fact the rank of A, the other way of looking at rank of A, or the proper definition of rank of A, is also the number of linearly independent columns of the matrix A, because the number of linearly independent columns of the matrix A will essentially form a basis for the column space of A, and we know that the number of elements in the basis is going to be the dimension, and the dimension is what we call as the dimension of the column space is what we call as the rank of the matrix A. So these 4 fundamental subspaces are always there associated with a matrix. Now what we want to do is we want to introduce one more subspace, basically with a different extra operator, which is what you call, it's an extra operation that we are going to give it to the vector space. So we already know that a vector space is equipped with this operation of vector addition and scalar multiplication. Now what we do is we add one more operation to it. The fundamental operations are vector addition and scalar multiplication. Now what we do is we equip this vector space with another operation called the inner product operation. Remember, when we did inner product or dot product, we were always looking for the dot product being 0. If the dot product is 0, then we say that the vectors were orthogonal to each other. Now we have this question, what is that? Suppose I give a vector, suppose I give, let us say a subspace, a vector subspace of a higher dimensional vector space. I want to look at the set of all those vectors which are orthogonal to this subspace that we have already taken out of the vector space V, or the higher dimensional vector space. The question is, will that form a vector space? Because that is again going to help us in putting things in a formal manner, looking at the orientation of the 4 fundamental subspaces that we had. So the question that we have now is, given a vector subspace of a higher dimensional vector space, look at the set of all those vectors which are orthogonal to this vector subspace. Will that form a subspace, yet another subspace of the same higher dimensional vector space? That is what we are going to look at. Let us work out with some examples. Let us look at certain examples and then see what happens. If this exploration or if this journey is even worth it. If it is worth, then there is something interesting. If it is not, yeah, then if the journey turns out futile, we will say that okay, the set of vectors which are orthogonal to given vector space, a subspace is not going to be a vector space. So we will, the chapter gets over there. But let us just try looking out some examples and see where we go. Okay. Let us consider this case, example 1. Let us take just this x1 plus x2 is equal to 0. Now if I say x1 plus x2 is equal to 0, what am I basically looking for? Solve for x1 and x2. Let us take this, solve for x1 and x2. Now what is x1 plus x2 equal to 0, what does it correspond to geometrically? Let us look at that. What does that mean? x1 plus x2 is equal to 0 corresponds to what is that? The line we have 0 comma 0, 1 minus 1. Let us mark all these points. It's 1. So I have 0, 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3, minus 4, 1, 2, 3, 4, minus 1, minus 2, minus 3 and so on. Now what is the geometry of this x1 plus x2 is equal to 0? It is going to be a line passing through the origin and through the point 1 comma minus 1. Now we already know that a line passing through the origin is basically a subspace of a higher dimensional vector space. So for example, in this case this line is basically a subspace of R2. Right. Now if you carefully examine this equation which says x1 plus x2 is equal to 0, it is like saying I have this vector, let us say this is 1x1 plus 1x2, the coefficients are 1 1. So what does it say? It is basically saying, look, I have this vector 1 comma 1, I have this vector x1 x2. What I am asking for? What am I asking for? I am asking for that set of vectors which are going to be orthogonal to the vector 1 1. That is what I ask for. That means I am looking for the set of vectors x1 x2 such that they are orthogonal to this vector 1 1 and it's orthogonal to the vector 1 1. So how did we actually get into this 1x1 plus x2 1x2? It's basically saying I'm going to look at 1 1, the transpose of this vector with x1 x2, and that's equal to 0. What is 1 1 transpose? It is basically the row vector 1 1 and you have x1 x2 which is basically giving me 0. The dot product has to be a number, real number, so you get 0. So this gives me x1 plus x2 is equal to 0. Now essentially what am I asking for? I am looking for a set of vectors or another vector which is basically orthogonal to this vector 1 1. Now what is the set of vectors? What is orthogonal to this vector 1 1? What is it orthogonal to this vector 1 1? So we have, so the vector is, this is the vector 1 1 that I have. If you take every vector, every point on this line, that is going to be orthogonal to this vector 1 1. Is that right? Any point on this line, let us say any point on this line that you take, which is like say 1 minus 1 0 0 minus 1 1 2 minus 2 minus 2 2 and so on, will be orthogonal to this vector. Is that right? Yeah. So now what are we going to say? We are going to say that, look, that means the set of vectors, let us say this, the set of vectors and what is interesting is it is not just about this what would you say, this vector, let us say 1 1, you take any point on this line which is passing through the origin and through the point 1 comma 1, you will see that that is yet another line that we have which is passing through the origin, and you have this line which corresponds to the multiples which correspond to the line passing through the origin and the point 1 minus 1. This entire line, the points on this entire line is going to be orthogonal to the entire line that you have which passes through the origin and the vector 1 comma the point 1 comma 1. So which means it tells us that, look, the set of vectors orthogonal to a given what we call subspace looks like another subspace. Let us take another example. Let us take this example. So what is the second example that we want to take? Let us look at this. Example 2. Suppose I have this x1 plus x2 plus x3 is equal to 0, or let us say x1 plus x2 plus 2x3 is equal to 0. Let us take this. Now what am I looking for again? I am looking for, if you take the coefficients as 1, 1 and 2, that is precisely the coefficients of these x1, x2 and x3. So what am I looking for? I am looking for the set of vectors orthogonal to the vector 1 1 2, right. I am looking at set of vectors orthogonal to 1 1 2 because what I am saying is 1 1 2 dot product with x1 x2 x3 gives me 0. That is what this plane actually means. And this plane, it says the right hand side is 0, this plane passes through the origin in R3, right. Now what we have is the following. So what we have, x1 plus x2 plus 2x3 is equal to 0. Now if you take the row reduced echelon form, it is just going to be this matrix 1 1 2, right, into x1 x2 x3 is equal to 0, which means we have only one pivot which corresponds to x1 and the other two are free variables. So what am I going to have? So I am going to take x3 to be equal to t and x2 is equal to take s, parameterize it. So what am I going to have? I am going to have x1 is equal to minus s minus 2t. So the solution to this system of equation, the solution is basically, the solution to the system of equation is basically the following. What is that? It is x1 x2 x3 is equal to minus s minus 2t, s and t. Yeah. Now what we see here is the following. So we have the solution to be minus s minus 2t, s and t. Now you see we can write this as s into minus 1 1 0 plus t into minus 2 0 1. Now if you look at this, these two are linearly independent vectors, because if you can very clearly see that this vector is basically in the, let us say, x1 x2 plane, the third component is 0, and this vector is basically in the x1 x3 plane because the second component is 0. So let us write this in x1 x3 plane. That means these two fellows are linearly independent vectors, and we know that a pair of linearly independent vectors will actually span a plane, and it will be a plane through the origin. It is a plane through origin in 3 dimension right now. And what do we know about a plane through the origin? A plane through origin is a vector space again. So what did we find? We found that the set of vectors which are orthogonal to that given vector, which was like 1 1 2, is basically spanning a plane. It's the set of all those vectors which are on this plane defined by -1 1 0 and -2 0 1, the linear combination of these two vectors. The entire plane is orthogonal to that one particular vector, which was basically 1 1 2. Not just that, you take any multiple of that 1 1 2, we will see that the plane, the vectors which are in this plane will be orthogonal to any multiple of that. Is that right? So because we know that, recall that if u and v are two vectors, then we already know what is u dot v. We know, then what we do is we multiply this vector u by a scalar c. Then let us say for a real scalar c, the dot product of cu with v is the same as the dot product of u with cv, the dot product of u with cv, which is the same as c times the dot product of u comma v. Now what do we see here? We see that if u dot v is 0, then we will see that cu dot v is also equal to 0 for real scalar c. Is that fine? Let us look at the next example. So which means in this case we found that this is a plane, so the set of vectors orthogonal to one 1 2 is on the plane, or is the plane passing through origin and defined by this -1 1 0 plus t into -2 0 1. Yeah. Now let us take one more example. What was the example number? Let us take example 3. Example 3. Let us look at this x1. Let us even make this generic, then we will understand better. So we will have a1 x1 plus a2 x2 plus a3 x3 is equal to 0, and b1 x1 plus b2 x2 plus b3 x3 is equal to 0. what is it that we want? In this case what we want is, we want that vector x1, x2, x3 orthogonal to both a1, a2, a3 and b1, b2, b3. What is that vector which is orthogonal to both these vectors? Remember, when we got into the 3-dimensional case, we figured out that if you have a pair of vectors, the vector which is orthogonal to both these vectors is basically the cross product of the two vectors. You remember we did this. If you have, let us say, your ij, therefore the vector which is orthogonal to that is basically along the direction of k, which is obtained as the cross product of this I cross j. Is that right? So we find that, okay, so what we do here, we say that the cross product of a1, a2, a3 and b1, b2, b3 will be orthogonal to both a1, a2, a3 comma b1, b2, b3. Yeah. Now not just that, any line passing through the origin and through the vector which is defined as the cross product of these two vectors will be perpendicular to these two planes, the plane that we have here, right. So what is interesting is, if you look at the set of all those vectors, oh, let us take one more case and then figure out whether it is true. Suppose I take this, let us consider one more example, example 4. I have 2 x1 plus x2 is equal to 0, x1 plus 2 x2 is equal to 0. Now what we want here is basically that vector which is orthogonal to 2 1 and 1 2, right. We want that vector which is orthogonal to 2 1 and 1 2. So we want x1 x2 orthogonal to both two 1 and 1 2. Unfortunately in this case we cannot define the cross product, because cross product has to be in a direction which is orthogonal to both the vectors. So that idea we cannot use here. If you have 3 dimensions, we can actually talk about cross product in 3 dimension, because you will have 2 vectors and the third vector can always be in the direction orthogonal to both. That is a new that's something which we can do. In this case we can't do. Now what is that vector which is orthogonal to this? We already know. This is equivalent to saying, finding out, solving the system of equation, the homogeneous system of equation where I have Ax is equal to 0, and I already know the solution for this. What is that? The solution to this is basically x1 is equal to 0, x2 is equal to 0. So that is the only vector which is orthogonal to both these vectors 2 1 and 1 2, and that one vector which is 0 comma 0, you know, that is a subspace of R2. Yeah, that is a subspace of R2. In all these cases that we have seen, we found that if you are given a vector space, so what is the vector space here, what is the subspace here? The subspace is basically the entire R2. Is that clear? So the subspace that we have is entire R2. What are we asking for? We are looking for, we want set of vectors orthogonal to orthogonal to every vector in R2. We want that vector which is orthogonal to every vector in R2. What is that vector? The 0 vector. Okay. If you have the entire plane, the only fellow which is orthogonal to every other fellow is the 0 vector. So, this set now has only the 0 vector. And therefore, that set 0 comma 0 is a subspace, of R2. It's a subspace of R2. So, what do we see here? If we are going to define something here, we are going to define what is known as the set of vectors. So, let us write this definition. Given a vector space V, let us say of dimension of dimension D. We do not even know, it could be entire Rn, in which case the dimension is going to be n, but we just put any generic dimension. Let us say it is a vector space of dimension D and a subspace W of D, of the D dimensional vector space V, right, a subspace V W of V. We can find, we have, or say we define the orthogonal complement, we define the orthogonal complement subspace of W as the set of vectors in V which are orthogonal to W. Right. So, this orthogonal complement subspace is denoted as the orthogonal complement subspace. Subspace is denoted by W perpendicular. This is clear, W perpendicular. Let us take some example. So, let us formally write mathematically. So, W perpendicular, let us write this for let V be any vector space, V be a D dimensional vector space, and W be a k dimensional subspace of V k dimensional subspace of V, W complement, orthogonal complement, is basically the set of all vectors, let us say the set of all vectors x such that x dot w is equal to 0 for every w, every vector w in the subspace W. Is that okay? X transpose W is equal to 0 or x dot W is equal to 0 for every W in the vector space, the subspace W. Let us take some examples again. Let us look at some examples. Example. Number 1, the vector space V is R2. The vector space W is basically the set of all those vectors which are the set of all those vectors whose first component is non-zero and the second component is 0. What does that mean? This is basically the set of vectors along, it is basically the line passing through the origin and 1 comma 0, the vector 1 comma 0 basically along the x axis. So what is W perpendicular? W perpendicular in this case is basically the set of all those vectors which are on the y axis. So I am going to have, or the x2 axis, 0 comma x2 where x2 is real, and you can see that very clearly when you look at the graph sheet, your x axis and y axis are basically perpendicular to each other, right. You see that W is basically this corresponding to the vectors on along the direction of x axis, and you have W perpendicular to be the set of vectors which are along the y axis. So these two are orthogonal complements of each other. Is that okay? Second, let us take some more examples. Example 2. Let us take V to be R3, okay, let us take V to be R2 and W, the subspace also to be R2, the subspace also to be R2, then W perpendicular. What is W perpendicular? W perpendicular is basically that vector which is orthogonal to every vector in R2 which is just the 0 vector, okay. That is the trivial subspace of R2. Example 3. V is basically R3, W I am going to define it as the set of vectors which are this. The set of vectors basically with the first component to be non-zero, the second two component, the next two components are all 0. That means this is basically along the x1 axis in R3. So the question is, what is the orthogonal complement for this? What is the orthogonal complement for? So what is W perpendicular? So what is the, we see that this is going to be the multiples of this particular vector is going to be along the line passing through the origin and through the x1 axis. So which is, what is the subspace which is orthogonal to this? That is going to be your x2 x3 plane, right, x2 x3 plane. So therefore that is given by 0 x2 x3 x2 comma x3 in R. right. We can actually see that 0 into x1 plus 0 into x2 plus 0 into x3 is going to give me 0. Is that clear? That means the set of orthogonal vectors. That means I am going to write now this is 0 x2 into 0 1 0 plus x3 into 0 0 1. You can very clearly see this is going to be the plane corresponding to the x2 x3 plane. So x2 comma x3 in R. Right, and we have already seen the other cases where you had two vectors in 3D. The third the vector orthogonal to these two vectors is basically the cross product and stuff. So we have seen all that. So therefore what we are going to conclude here is we are going to say that look, you can always find, given a vector space and given a subspace of the vector space, you can always find set of vectors which are orthogonal to this given subspace, and the set of vectors which are orthogonal to this given subspace also is a subspace of the entire vector space V. And what is interesting is we will see that the dimension of the vector subspace and its orthogonal complement is equal to the sum of the dimension or of the vector space subspace and the orthogonal complement of the subspace will add up to the dimension of the original vector space that you are looking at. For example, you look at this, W is R2. So what is the dimension of W? Dimension of W is 2. Now what is dimension of W perpendicular? It is just the dimension of the trivial subspace. We know the dimension of the trivial subspace is basically 0. So what do we see? We see this dimension of W plus dimension of W perpendicular is equal to dimension of V. We can see that here also. What is dimension of W? Dimension of W was 1. What is dimension of W perpendicular? Dimension of W perpendicular is basically 2, right. It is a plane, so it is 2. So what is dimension of W plus dimension of W perpendicular? W perpendicular plus dimension of W is basically 2 plus 1, which is 3, which is the same as the dimension of V. So whenever you have orthogonal complement of subspaces which are orthogonal to each other, we see that the dimension of the subspace plus the dimension of its orthogonal complement, they add up to the dimension of the vector space to which they belong to. Is that clear? And we can see that in the previous cases also, right. Like we took this example when we use R2, we just proved this. We had this examples and all, we looked at this also. This is the cross product of this two vectors is basically a line passing through the origin and in the direction of the cross product of the two vectors. The dimension of this these two vectors, if you take the dimension of these two the subspace spanned by these two vectors will be a plane if these two are linearly independent, in which case the orthogonal complement subspace will be a one dimensional subspace and so on. Now why do we need all these things? We will see in the next lecture that the null space of A and the range of A transpose, or the column space of A transpose, they are orthogonal complements of each other. This is something which we will look at in the next lecture. We will also prove that the null space of A transpose and the column space of A, they are orthogonal complements of each other. Again we will establish this. Once we do this, we will get to clearly establish this rank nullity theorem, and we will also be able to establish the fact that the rank of the matrix A and the rank of the matrix A transpose are the same. Once we do that, we will look at one more subspace associated with a matrix. Of course it is a special subspace in the sense it is this particular subspace is associated only with square matrices which are, let us say, you have the eigenvalues and eigenvectors associated with square matrices. Of course, not all square matrices will have real eigenvalues and eigenvectors. So, what we are going to look at the vector space, I mean basically what we call as the invariant subspaces or the eigen space. So, that is something which we will look at in next lecture. So, in the next lecture what we are going to focus on is basically we are going to establish the orientation between the two subspaces on I mean on each of these what do you call vector spaces Rn and Rm. We are going to establish the relationship between the two subspaces each on Rn and Rm corresponding to the fundamental subspaces associated with the matrix, and then we will quickly revisit this rank nullity theorem and establish that the rank of the matrix A is the same as the rank of the matrix A transpose, and then we will look at eigenspaces. So, that will complete this module, and then we will take up special matrices like I mean real symmetric matrices. We look at we have still not addressed that one case where the vector B is not in the column space of A. We have done it in 3 dimension, but we will do it in general because there's something more interesting that comes out there. So, that is something we will look at in future lectures. Thank you.